enjoying myself tremendously. And so, let me tell you a little bit more about granular materials. And so last time you saw this outline, and I told you about these two aspects right here. And today we'll add water. So now we're going away from dry grains and add just enough water to make mud-like structures, so suspensions, very dense suspensions. And I'll tell you about two things. Here we talked about how dry grains break up. We also remind you about how liquids break up. And then, in this case, what about the breakup of those things? And then finally, in the last part, we'll go into some shear rheology. Okay, so first of all, if you think about breaking a liquid into two pieces, so you start with a slender column of a liquid, and somehow by gravity, let's say, it comes out of a faucet, it gets ripped apart. It goes from one into two pieces, right? So this is really a catastrophic event for that water, but it's also topological. Right? And so these types of topological transitions that you see in liquids, they are actually accessible very nicely to high-speed cameras. You can also study them within the framework of the equations that were introduced here. And so they have become a model system to test very general ideas about this type of topological transition. So that happens, of course, in fluids, for various types of fluids. More generally, in condensed matter physics, where you pull apart other things, let's say very thin nanoscale gold wires, eventually also break. You know, this is pushing stuff to its extreme point, where it's about to fall apart. But then all the way, it turns out these equations have connections to what you have in black hole physics, you know, where also things eventually snap off. And then, of course, there's the technological relevance that often you want a puddle of water or fuel to be translated into a whole bunch of little droplets, right, for fuel injection, for example. So how do you control them? So that is, of course, connected to that. Now, in pure fluids, so no particles in that. In simple fluids, meaning no polymeric solutions, just molecular fluids, so very simple thing. There's types of structures that happen right at the moment where this transition occurs. They are very distinct. They are telltale signatures, in fact, of the underlying liquid type. So if you could look at this, you could say what that liquid is, right? And we'll look at that. And of course, this breakup will continue, starting from the macroscopic size of the cylinder until eventually the last molecules hanging, together by van der Waals interactions are pulled apart. And then that's over, right? It goes down all the way to the molecular scale. Now, by contrast, what I showed you with the granular system, there is no molecular scale. So the smallest scale there is the individual grain scale. There are also distinct shapes, right? Now you would have to average over those because each shape is a little different, of course, but you do an ensemble average. We talked about the statistics there. They are, of course, more ragged individually. You can typically see the grains because now we're 5 orders of magnitude bigger. But there's still some scaling. That was the big surprise. So I showed you this is 2/3 scaling. I told you we don't understand it, but it is there. And now you can ask yourself, what are the ingredients there? So previously in the slide you probably read that. The key ingredients are the things that distinguish or characterize any macroscopic parameters. Density, surface tension, viscosity. Here, it seems to be material density is some effective surface tension. Viscosity, you have to decide how you want to define it, but what I showed you is that the coefficient of restitution principle. Okay? And what I'm pushing here is that that's a really nice system to now look at things that usually are masked by gravity, namely these van der Waals type or cohesive bridges that happen on nanometer scales at short range, and they are if you order a few, maybe tens of nanometers. Right? So it's a diagnostic again, very nice. So okay, so these are the two extreme limits: all water, all pure simple liquid, all grains. So now we're going to say, all right, let's mix this a little bit. Okay, so you have a plate with mud. So here's a map. These happen to be really big particles. They're almost a millimeter in diameter, and they're in water. Zirconium dioxide. Doesn't matter. They're just nice and reflective. So it looks like some sort of a bunch of caviar. right? Fish eggs. And they're coming off a nozzle that's a few millimeters in diameter, and you see the glistening, so there's liquid in there, and it does this catastrophic deformation, and now it breaks up, and then there's a little bit of liquid left in the end, and then of course the last bit proceeds as a liquid topological transition, and I'm not interested in that, right? I'm just trying to go down to the point where the last two grains separate. Then you get you do satellite drops like that. So what is the effect of the liquid? That's what we're going to talk about. Now, how do we do these experiments? We take syringes, and much you can't push it out of a thick syringe into a small opening, so we just cut off the whole bottom. We use different sizes syringes, so that's one control parameter. We fill it with that mud, and we use the syringe pump and just push it out. It comes out like a plug, typically. It's really dense suspension. So these are suspensions of particles that are not necessarily density matched, so they settle. Okay? But we can also density match. And then this is kind of the sequence from this movie. Now, in contrast to the dry grains, this happens right underneath the syringe, so you don't need a free-falling camera going half a meter or whatever until it finally happens. So it's right there. It's very convenient. What can we vary? We can vary the size of the nozzle, size of the particle, type of the particles, so the solvent, viscosity, so water, oil, whatever. And typically people have looked at these suspensions of particles as essentially increasing the viscosity. So the first idea would always be, well, you put particles in it feels thicker, right? So it is probably just like it might be like a high viscosity liquid. So now let me compare a few things. So there's a lot on this slide, but it's actually repeated. So let's focus on this part right here. There's two rows of images. Time goes from early to closer to breakup here. And each panel is about an order of magnitude closer to breakup. So here we're about a second away from breakup, 10th of a second, and so on. And here, 10 to the minus 4 seconds, and this is kind of after breakup has occurred. This is a suspension, and it's backlit. So you just see, because it's opaque, you see just a dark blob. It's just the same thing that we saw before. Down here, I used an ordinary liquid, an oil of about the same viscosity, 50 centistokes in this particular case. And again, you start the second array, and then you get closer and closer to breakup. And here, you can hardly see that probably from the back, but an oil will pull a long thread. So you see this very, very thin thread. Now, since this pulls a long thread, it's a little hard to get the spatial and the temporal resolution. You have to be a little bit further away to see the whole thing. So what Mark Miskin, the student who works in that, did, and I'll show you in a minute the movies, we used a two-camera system, two synchronized high-speed cameras, one from the back, that's these 3 panels, and then another one from the side that zooms in just at where that happens. Since we know where it happens, we can already pre-position that thing and be ready for it, and we synchronize it. So I'll show you now a movie where you start out with the one camera, lower resolution, and then we zoom in essentially by synchronizing the movies. Yes?
The oil has the same viscosity as what?
Well, as the same effective viscosity as this
As the whole
suspension.
thing.
Okay, so now this row here corresponds, that's snapshots from this movie. This row are snapshots from this movie, right? Oil, suspension. Gravity goes down, the nozzle diameter in both cases is almost 5 millimeters, 4.7 millimeters. And this is, the particles are the same size, so sorry, there's no particles in here. This is 145 zirconium barrels. So little smaller particles in the movie I showed you before. So here we go. You see it very slowly necking, right? And now it breaks, and we're zooming in, and you see these particle protrusions there, little reflection, and then it breaks up. You can see the raggedness of the particles are smoothed out by meniscus, okay? Want to see that again? Okay, here you go. So you see a little bit of that raggedness from the particles, next down. Now we zoom in, you see some of the particles sticking out, and at the last bit you can even see through the liquid. That's still connected, right? Is that all clear? So now let's try the same thing for the oil. And now the oil will actually pull longer thread. Now you see that here, that's why this movie is longer. And there's the thread. It's about to break up. We're zooming in. Now the drop is of course really huge. This is a reflection focusing effect actually. And here we go, there's the breakup happening right there. And you pull that long thread. And if you kept going, then it would actually sever, right? So it is actually different. And obviously you can't see the molecules there. Now, what about the scaling now of the neck width? So that's the only thing I want to talk about. The width here, the width across this neck as a function of time. Obviously it has to go to 0 at the singularity, right? And the interesting thing is this is now work by Mark Miskin. This is his first year with me. Really exceptional student. The interesting thing is if you do that for the suspension, and this is one particular suspension, I'll show you many more. This happens to be 22 micron glass spheres in water. You get a beautiful power law. This is good over maybe 2 decades in time. It's actually going down to a frame rate of about 10 to minus 4 here. And right here is the particle diameter. So this is 100th of a millimeter. So somewhere is the particle diameter cutoff. And that prevents, of course, us from going further. The cameras go to millions per second. That's not the issue. Eventually we cut off by the particles. And so if you assign a power law, which is a log-log plot of the radius at the minimum as a function of time. Oh, and I should, first of all, let's orient ourselves. So the way these plots are done, this is a standard way of plotting things. They're done as a function of time remaining to break up, tau. So it's the distance in time until you hit 0. So in fact, you always read it backwards. You start over here, and the drop is big and fat, and then you go this way towards breakup, right? The radius comes down, the time goes to 0. So you have to read these things that way. Okay, so if you look at that, it's a 1/2 power law. No, it's a viscous power law. No, it happens to be this 2/3 power law again. And I'm just telling you, if you know liquids, pure liquids, you say, well, tell me the power law, tell you the liquid. This would have been viscous, totally viscous. The limit of the viscous liquid. This is what we find. Now, this is something where you exchange the liquid for a fluid, air. So you have a bubble pinch off. This is worked by, for example, many people, by, for example, my colleagues at Jaegar. Yes?
So you actually had these particles in water. So there was a little bit of water and then the suspension.
That's right.
What if you had actually in another viscous liquid? Then would
I'll
you?
show you the thing. So we can exchange the solid, the liquid. We can make this water, oil,
So
anything we want. And I'll show you in a minute what happens, right?
Okay.
So this is just the first example. And this happens to be a particularly nice way, a nice long power law, right? Now, a couple of remarks. All of these things are coming out of scaling theories, right? So that means they are good as you get close to breakup. That's where the theory shines. That's where the experiment runs into trouble, because close to breakup, measuring things becomes very, very difficult. That's why we have error bars here. So this is always this trick. How far away can this still hold? And if you did water, and the best people who have done the best measurements on water, they will show you the data that very close to the initial state. Of course, this water that actually would be, in fact, this thing here. It would not be a 2/3 power law. Right? So did I say that? I said it last time, right? 2/3 would have told you it is like water. If you had closed your eyes and I told you 2/3, they're sure water. It's not true, right? It's particles in it. What is it?
How precise is the determination of T0? Because you need to know it to.
Yes.
If you move it a little
Right.
bit, I guess it changes
Right.
the exposure.
And so, of course, this is an experimental issue. It's a very good question. How precise is T0? Well, if I move T0, then you'll get, of course, you can get different power laws, depending on the range of data. What you try, this is the game, is you try to get the largest range you can, trying to stay away from considerations like large errors here, theory not applicable out there anymore, and what will not follow the equation. I'll show you in a minute. It depends. So early on, the boundary conditions matter. Scaling and self-similarity means that eventually this thing forgets where it came from, and then always follows this power law. But initially, of course, it came out of a faucet of some distance, the diameter, and it knows that, right? So initially, there's always trouble. This you want to make as long as possible and the error bars as small as possible. And if you change T naught a little bit, you would get curvature in here, right? Just from on the data. And so that is an experimental problem of doing as good a job as possible. Yes, Jim?
And so I was curious, it looks like some of your lines are intersecting on this plot. Is it because there's an additional fitting parameter in
No,
the
so-
pinch off scaling, or is it just for visualization?
With the lines intersecting on this plot, you say?
So look on the left,
Yeah?
further down towards breakup.
Yeah?
So you have your
Oh,
dash
these
line.
here.
Yeah.
Oh, okay. So, yes, there are 3 lines shown, 2 dashed lines, 1 solid line. The solid line is actually the best fit to the data, assuming that there is a power law. Right? We assume there's a power law, and we say what would the fit be. Okay? The other 2 lines are just for illustration of a power law, and you can shift them up and down as much as you want. I'm just trying to illustrate what would, on the same scale, a power of 1 look like and a power of 1/2. And you see that our data has uncertainty in it. It is not perfect, but it is not so bad that you can't distinguish these things from each other. So 2/3, 0.66, and 1/2, or 1 are clearly different on this plot. So you cannot tell me our data can't distinguish between these 3 behaviors. That's all I want to show you, right? So these are just for show. If you don't like the intercept, move it up. It's just a scale. Okay? So good. So this is very interesting. Totally unsuspected. Huge surprise for me. And I don't know if anybody's ever predicted what that's maybe. There's one group, Eric Clement, who has recently said that over certain ranges it looks like data of this type is compatible with original base. Right? Yes, Jim.
I'm surprised that there was theory for the suspension.
No, there was no theory for
Oh, I thought you said there was.
Okay, sorry, that's a good point. So what is the theoretical status? For liquids, there is theory, scaling theory. For pure symbol, for suspensions, there is no theory that I know of in this dense limit. Jeff Morris has done some really nice work putting a very low number of particles into the threads. And then eventually, at the singularity, since this thing comes down, even 1 particle will make a difference, right? Because the radius comes down that you can trap. And the people who do inkjet printing are, of course, very interested in this, right? There's particles in a liquid. But inkjet printers use maybe up to 10-20% of volume particles. Here we're in the dense limit, so there's nothing that I know for the dense limit available. And the only other thing that people have worked on is bubble pinch off. So now you have a bubble going up in water, let's say, and it pinches off. And then you get 1/2. Okay, so this is new territory. I'm doing this. I'm showing you data. I will give you a model that we cooked up. And we're very proud of it, and I want you to critique it, okay? It's actually really cool. I'm getting ahead of myself. So now I'm showing you a whole bunch of data. This is meant to tell you we tried a lot of things. And it's meant to tell you no matter what we try, asymptotically, the 2/3 power law is robust. And we can talk about details, but this is meant to just overwhelm you a little bit. Okay? So what did we try? We tried glass in water in different oils. So we changed the viscosity, there was a question, right? By a factor 100 or more. And you know what? The power law stays the same. Right? In fact, if you change just the viscosity of the solvent, nothing whatsoever happens. If you change the solvent itself, you go from water to oil, actually something happens. It's a slight shift. I'll talk to you about that later. But the power law itself is pretty good. Now this is what happens initially, right? Even for water. So this always happens. There's no theory for that. It depends on the initial conditions. But this is what we're interested in. Now what else can you do? You change the nozzle diameter. Still gives you power laws. Well, things happen at the beginning, but eventually it's always a power law. What else could you do? You could change the size of the particles. I'm showing you 2 representative curves here. Still the same power law. And then you can say, well, let me just now quantitatively compare a suspension with a oil with the same viscosity. You do that in a rheometer. Just say, make it the same viscosity by putting enough particles in. And there is some range over which these things coincide. But then the oil down here goes to where it wants to go to, namely the linear scaling, which is this blue dotted line, and there's a prefactor which actually works out. You know viscosity. And the suspension here in red just keeps going on the 2/3. Right? So this is really robust and really remarkable. And now the question is, where on earth does this 2/3 power law come from? Because it is not just an inviscid liquid. I mean, that clearly can't be it. So it's some sort of coincidence, or there's something deeper behind it. Okay?
I'm sorry, did you say what the volume fractions are?
Yeah, so the volume fractions are in the order of 50%. And actually, we can look at this down to maybe 30%. It still survives. But we're looking at the high end, close to jamming, 50 to almost up to 60%.
Wait, so how do you keep the volume fractions constant?
No, we don't. So this is by settling.
Oh, okay.
Or, I mean, you can, with very much effort, you can prepare something that's density matched. But in this case, all the time scale is, in fact, the time scale for this breakup overall is seconds, right? I mean, you load this thing, you push it down, in a few seconds you're done. If we do it right with the density match, let's say the settling time for anything is much longer, so we don't have to worry about settling. So, now one thing that do you have any question?
You're density matching the particles to the fluid?
But not always. So we have done it, and we find it doesn't matter whether we density match or not, because
This is falling in air, so I don't see why it would matter at all. Are you expecting
No,
relative motion between the two?
now we're worried that you might be worried that something already in the syringe kind of settles out, and that different densities throughout the system, so as you push it.
Just,
And it doesn't matter over the time scale.
it's just neurotic precaution.
We love to have neurotic precaution, because, you know, since there is nothing out there that says that you have to expect 2/3, we go like, gee, you know, let's be neurotic. But one thing we don't have to be neurotic about is we can just stare at the movies and we say, look, as this thing comes in, obviously towards the end, but even before, there is an interface between the liquid and the air, and the interface involves one outer layer of particles. Now the outer layer of particles, they are special, because they're not fully submerged in the liquid. I mean, the liquid is everywhere inside, but the outer ones, they have menisci. And that got to play a role, right? And the granularity has to come in somehow. And here's how I do. This is now towards a model, okay? So I say that particles of two flavors, one's in the interior that are fully submerged, and they contribute to the weight of the drop, sure, right? The mass. But this is so slow in some sense, again, it's a fast process, but it turns out viscosity, as I showed you, did not matter. Oh, I don't know, did I say that? Let's go back to here. So the one thing, there was a question, right? And you asked that. The one thing that I really, really insist on, viscosity of this solvent does not matter. Fact number right here. Yes.
What about surface tension?
Yeah, the surface tension will matter.
Is this all perfectly wetting?
So it will matter, and surface tension is the key ingredient, right? But you know that from dimensional analysis already. If you have a T to the 2/3 power law, I showed you that last time, and you have width and you have time, you know, you want to do dimensional analysis, surface tension is key. Surface tension, but not viscosity. I'll show you how surface tension comes in. It's absolutely the key parameter. It's these menisci, right? Give it away, sure. They are linked here, these little blue guys. I don't know if you can see them. So now let's have a conductive experiment. Let's suppose this is it, right? The particles are inside, the menisci hold this together. Let's suppose I just put uniform pressure everywhere on a column of this stuff. Uniform pressure. If it's pretty dense, granular again, well, there's nothing that's going to happen. It's just touching each other, the particles. So you don't get any flow from that. However, what is the pressure on the outside if you had a column like that? Well, the pressure is the pressure produced by these little menisci. You know, depending, of course, on details like wetting, that's this alpha right here. You can put in wetting angles quantitatively. I'll show you at the end of this. But it's really surface tension divided by the characteristic scale, and that is the scale of the particle radius. Okay? And the prefactor turns out to be about 1/10. So that's the pressure. Now let's suppose I wanted to induce flow. What would I do? I wouldn't just press everywhere. I would just pinch it, wouldn't I? Imagine a sack filled with a sausage out of sand, you know, and you pinch it and it goes this way. So if you have a pressure gradient, you can get flow. So this is key. Now imagine you go back to the movies and you say, well, what really happened is this happened. There was a negative Gaussian curvature. Now, particles on the flat surface have just a constant pressure. But particles on a curved surface, you can imagine that the pressure will vary depending on the curvature. So this is really interesting now. The curvature of the surface containing particles now might induce a difference in pressure. So what drives this then is that once you got a curvature there, that the pressure will vary, and it will actually be larger right here where large curvature occurs, and it will pinch it up that way. Okay? So now we're going to basically use the fact that these particles are there to say that the surface tension over A component of the pressure is not constant throughout anymore, but will depend on the curvature.
There are two components of the curvature, right?
Yes.
Which component are you talking about?
And which components do you mean?
Well, you seem to be talking about the one shown in the plane of the page.
In the end, it turns out, so it's Gaussian
But
curvature.
the other one is,
Yes.
is a small,
Yes.
bigger curvature.
Sorry, you're right. Thanks. So what will matter is Gaussian curvature. And Gaussian curvature, okay, is 1 over the radii of the two principal radii. And if you have something like this, you got one principal radius here, R0, let's say, and you got another principal radius, Rm, so that's the minimal radius at the snap off, right? And the smaller one will not. And so this is what that's going to be. And I don't have time to actually show you why it is 1 over R0 there, but if anybody's interested, we can actually have a good argument why that is. So in other words, this will actually, you can experiment it, you can show that experimentally, stay more or less constant. Well, this radius will of course come down, right? Okay, so the idea is then to start with the Navier-Stokes equation. Some way. Use the fact that viscosity is irrelevant. Use the fact that it's, so basically means irrotational flows, and use the fact that the volume has to be conserved, so no particles are jumping out. And you know, reasonably, I would say you can go from here to this. Now there's a couple steps in there that are interesting, and you know, I don't have time to tell you about it, but basically the key thing is that in order to get flow, and it's going to be flow this way and that way, you need a pressure gradient. So a constant pressure could do it, right? And the gradient of this pressure will come from curvature. So this is then the remaining question. So what is the pressure then as a function of curvature? So as I go in the z direction, up and down, the pressure presumably is going to change. And I'll tell you that's because the curvature here and here is different because of how tightly you pinch it. Yes?
Are you thinking about pressure in terms of capillary attraction
Yes.
between particles,
Yes.
or just the
Just this pressure.
curvature of the liquid itself? between
That's
particles?
just the pressure coming from the capillary interaction structure. So basically, here's the idea. This is a lot of stuff, so let me go through. I told you that that's the concept. You know? So curvature will mean that the pressure is not constant in this direction, and then you can get flow. So now, in order to get the pressure, you use the simple equation that I have for a flat surface, namely that the pressure is just some 3 factor times gamma over A. Right, that's for one of these interfaces. One of these menisci. And say, well, how many menisci do I have over some typical area? And they would all push in. So you can count menisci, but that depends on the particle packing. The more particles you have, the more menisci you have, and also the tighter they are, right? So this is now reduced or converted to a really interesting problem, namely the packing of particles on a curved surface. Now on a straight surface, particle spheres pack hexagonally close, right? So you know the pattern. And what about a curved surface? Soccer balls, right? You notice there are 5-fold pentagons in there. So suddenly the packing is not hexagonal. So the density of particles changes, the density of menisci changes, therefore the curvature, it induces different types of pressure, right? And if you think about this type of curvature, so negative curvature, you can actually show that the pressure, it has this wetting prefactor, has the surface tension, has the particle radius, has the Gaussian curvature now, which really, this is the one that matters, this radius, the small one. And then it has here some factor that has to do with the packing. So Dave Madsen worked that out for flat 2D space, for any pack, including disordered packets. And so what it is it's a correction. It's 6, that's the order number, 6 nearest neighbors. And then the average coordination of your particular packing that you have. Let's say there's some missing. Z bar is the coordination. But on a curved surface now, it's not clear what Z bar is going to be. In fact, I don't know if anybody calculated it yet. So Mark then went ahead and found the average Z as a function of that curvature, Gaussian curvature. So we used some computer simulations with it and some arguments. Actually really cool. And it's a mess, but you can expand it near small curvatures. And this is the result in third order. It's actually an interesting result. So it says that if you have some curvature, the pressure is going to be what you get from the flat space. That's that part. And then there's the first part here that depends on the radius, right? K. And then there's some higher order correction. So now you plug that in, and the gradient says that you want to use this term here. And here we started, we plug that in, and so there's some prefactors, but the important things are, again, something with wetting, something with surface tension, this curvature, Gaussian curvature, and the particle radius. So that goes all in here, right? And then I plug in what K is, and it is 1 over Rm times R0. So you see that in the end, you got an equation that tells you in time scales and length scales how this radius will change. And one thing I forgot to say, so in viscosity this is irrelevant in here, right? The only thing that opposes this caving in is inertia. You know, if the part is being pushed out. So this is the inertial part on the left side, and this is this meniscus driven pressure on the right side. Now you reorganize that little bit, bring that over. You see there's an R, there's an R squared, that gives you an R cubed. And then you get a T squared here. So out of this emerges exactly the scaling law. And the good news is, I mean, okay, so 2/3 scaling, once you have no viscosity, that you would have guessed. But this is really interesting. We have to prefactor. So what does that say? How many of you know ordinary liquid breakout? Okay, I will have to talk about it. If you just had the dimensional analysis, right? And I showed it to you last time, this would have been a difference. You have still this? I mean, no viscosity, surface tension density. It's exactly what was in front of the thing last time. But it's A over R0. So this is a scaling law, but it knows something about the boundary conditions. It doesn't forget. So it's an interesting scaling. It's not that self-similar scaling that you have from the ordinary liquids. So this has memory. And now we can test something. So now you can plug things in, you can rescale your data and see if it all collapses using this, right? Yes?
What,
A couple of questions. Whoever.
What is R0?
R0 is the size of the nozzle, which turns out to be, and I don't have time to show you that, the same as this. So if you have a nozzle that has, this is the nozzle here, right? That has this R0, it turns out it's the same size as the one of the principal radius.
But that looked like it changed in time on the...
Yeah, but we have data to show you that that's actually not changing. Yes.
Do you think this would stand if you add some predisposity?
If I had what?
If you add some predisposity to your particles?
If I add additives?
Predisposity.
Oh, polydispersity. I would hope so, but I don't know. I mean, so in other words, as long as it's C bar here, I think that'd be fine, but I don't know how, I mean, you would have to put that in.
For what of finishing d'accord, there is also a memory effect.
Pardon me?
If I don't say something wrong, I think there is also memory effects. It shouldn't change the quantity.
So for the pure liquid, there can also be memory effects. Under certain conditions, if you go, and I have to remember this, certainly not for the inviscid case, right? Maybe for certain viscous combinations of inner and outer fluid. So, for example, if the inner fluid is less viscous, so you have the bubble, right? Then clearly there's memory, right? But for the inner fluid being more viscous, I think it's without memory. So simple oils will have no memory of the initial condition. And that's the beauty of the scaling theory. You don't have to worry about where the thing came from. Here, you will. So, but good. These are great questions, and this is our approach now to explain this, right? We're really excited because it explicitly puts the particles in there, and actually particle packages and curved surfaces, a little differential geometry. But it could be more fun to get that out of, or connected to droplet process. Yes?
So the average coordination number that you're measuring, is that in the cold and not on the
No,
outside?
that is only on the outside, because anything that what we claim, the only thing that drives this thing is the outside. In that sense, we got lucky. You know, if it would have been the inside, we could have never known.
So it's a two-dimensional measurement.
This is a two-dimensional measurement on a curved surface in 3D where the interior packing is disordered, so the particle packing on that curved surface is actually disordered. There's no theory for that.
So why are you comparing it to 6 and not 4?
Because it turns, why would it be 4?
I mean, in 2 dimensions, usually I imagine
two
the reason
dimensions,
is because you're
usually
comparing
six.
it to, right.
It's 6.
In 3 dimensions,
No, it's not true. It is a two-dimensional surface, and anyway, it's not 4. I mean, no way. In fact, it turns out it is larger.
you're not comparing it to the isostatic contact number?
No, I'm comparing it to the actual contact number. So in fact, we did computer simulations of the packing where we used the hyperboloid surface this thing runs on. We know the surface shape, and we put the
Oh, you're
particles-
comparing it to the hexagonal. Okay.
So the comparisons with the hexagonal, the actual numbers turn out, so Nelson says it's 6.02 or something like that for typical disordered systems. We find it is more in the 3D system, maybe 6.3, something like that. So it is slightly bigger than 3, but and 6, but not much. 10% max.
What do you see this pressure doing to the particles? Does it push them to the outside of the fluid? Does it expel them from the fluid? What is its physical effect?
It'll squeeze them out of the zone.
It sounds as though it's almost like it's implying there's like a plug flow up through the middle where you have very little relative motion, the particles are being pushed up, so you don't get much viscous response out of it.
Yeah, so what Mike says, is a blood flowing here? You know, maybe that's why there's no viscous response. Basically, the model is most easily for us rationalized by thinking about a really dense pattern where the particles are almost touching. Right? And yes, then not much is moving in there to begin with. Right? Can we prove anything about the interior flow? No, because we don't have X-rays yet to look at that as it moves. And I just bought myself an X-ray machine to do that, but we may not be able to get to the last stages of breakup because they're too fast. But we can put it in one of these instrument machines, and we'll do that. It's going on right now, where we can move it up and down, back and forth at will. And then I can look at the interior. So now the question is, does this hold water off, hold particles? I mean, does it actually work? And you have this prefactor now, and you can scale everything on top of this bunch of data. I showed you different radii or nozzle, whatever diameters. And it does a really nice job. So if you don't do anything, in particular to this factor alpha, there's this wetting question, right? Then this is a beta collapse. Now, as I said at the beginning, don't even expect collapse for water, so that's not a surprise. These slopes are all 1/2. Sorry, they're all 2/3. So I can't get that one. This is this 2/3 scaling. But there are some groupings here. I mean, it's not true that everything collapses exactly on the same curve quite yet. And if you scrutinize it, you find out it has nothing to do with different viscosities, sizes, nozzle diameters, but it has to do with chemistry. So particles that are glass with water, oil with glass, whatever, they lie in different bands. And so what that says is basically that alpha parameter in front of the surface tension that depends, of course, if you go in there on the wetting angles, right? And you can actually do that here, so this, you call it lambda, you know, sorry about that. So if you look at that for different materials, material combinations rather, there's a slight variation and that can be estimated, and the data fits pretty nicely on top of it. So here I'm using three representative curves, like this one, that one, and that. Okay, so it's a pretty nice collapse. So it works very, very well. Okay, good. So a couple more questions. So, hey, how about that? There are particles in it. What if I let the particle values go to zero? I should recover, of course, the ordinary liquid, right? Wait a second. That can't be right. You look at this and you say, did that go to zero? I don't think so. That's not the right limit. What this would say is to get to just this factor, you need the particle radius go to the nozzle radius. You make the particles huge. That's the right limit to recover water. So let's do that. So I have here water, and I have here really huge particles. How big were they? Maybe a couple hundred microns. You can see them with your eye. And now I'm superimposing exactly the shape of this thing on top of it. Mark, I can do it, right? And it does a really nice job. So let's do that one more time. So this is just etch finder, put the shape on top. Of course, this thing is more cylindrical at the beginning. And then it slowly goes. And if you measure, in fact, the R min as a function of time, and I hope this is really slow, it's a suspension. Let's go out. Okay. And if you measure actually and put these data on top of each other, they do a pretty good job. Now, remember when we do some ensemble averaging, of course, this was just for one problem, so there's some deviations. Here we go. It's slowly moving in, and eventually it should be going. And there we go. No. Suspense. There you go, right? It does a very nice job, and if you ensemble average, actually, or many, many drops, it works really, really well. So, okay, so let me sum that up. So, I think that this is quite neat because it splits the difference between grains, dry grains, and liquids in a new way. It's the grains on the surface and their organization on there that actually drives the dynamics. What comes out of this is something that's not self-similar, so it remembers particular nozzle size, but it has some scaling where the viscosity is not important. Right? And that is different from what's usually assumed. And maybe for many applications that could be just fine, but not for breakup itself. Right? And then the one thing to remember is, of course, eventually there are two particles by little liquid thread, and once that goes, then it's just liquid breakup from the right? All right, so good. Okay. Yes?
I just have a quick question. In the model, the key physics, as I understand it, that drives this breakup is the fact that you have a capillary pressure difference. The curvature of the menisci is different, and that drives this flow.
And the curvature is different. So this curvature, as you go along, differs, and that drives it.
So you showed, I mean, your particles are on the order of tens or hundreds of microns.
Yes.
And you showed these images where you had backlit, so you had a sharp contrast.
Yes.
Is it possible to directly image those little menisci and image the variation in the menisci curvature?
It's a great idea. So we haven't done it yet. We'll have to see. It would be a great thing.
Because that would be a direct demonstration.
Yeah. Yeah. So we'd love to do something like that. We haven't done it yet. Yes.
So I was a little confused about the equation for pressure few slides back, the expansion that you did. So what you expanded in was, I guess, some kind of non-dimensionalized Gaussian curvature.
Yeah, it's k minus k times a.
So isn't that blowing up as you approach the singularity?
Yeah, but you know, you always cut off the So you expand around. You expand around this point. That going to zero. That's right.
This goes to zero.
Yeah. That's the point around which you expand.
The RM is going to 0, isn't it?
Because he no longer considers it a suspension.
More questions? Yes.
In the first slide where you showed the granular drop and where you had that series of 6 on it, that granular drop looked like it was kind of hexagonal. Kind of a funny shape.
Which is this here?
Yeah.
Yeah.
So is that common or is that just happen to be?
Okay, so these are really dense suspensions. They're like thick toothpaste. So whatever you happen to start with at the bottom, it kind of stays there. When they come out as a cylinder, so in this case, I don't know what happened. Maybe you didn't mop it off. Now, when you make them thinner and thinner, more water and more oil, right? Then they do eventually become a little rounder because surface tension can also deform it. Good. More questions? Okay, so now we'll switch gears in terms of style. Less quantitative, more fun. If that, but same idea, right? We still have particles and liquid. And so one of the things I've been fascinated with is this question. So can you walk on water? I mean, this is not the typical thing right now, but we'll see what you can do. And in fact, it turns out it's water in quotation marks. I mean, not pure water. Right? So what would you do? Well, you could try this. That works. But that's not what I'm after. And that works really well. You could try this. That's a spider on a surface. Right? This is your surface tension. Again, it turns out if you put in numbers, you can have a spider that weighs about a pound. I mean, really scary thing. But you could not walk on water that way. There's just no way. Right?
How many legs does it have?
And how many legs? That's the other thing. It's just a little bit difficult. But animals, of course, they can walk on water. So here's one. Right on the top, that works really well. And now, let me just, so let's have some fun.
It's too loud.
Comes from the sky.
Oh.
Dark shapes overhead make it nervous. A hunted bird might expect it to flee to the trees. In fact, it does the opposite. This skitter across the surface of the water earns it precious seconds and the nickname Jesus Christ Lizard.
All right, so this works, right? And why does it work? Because
it drags its feet down so hard.
Because, just this silly thing.
Even than a few inches. A human would need to run at 65 miles an hour to do this.
Okay, good. Let's try that.
A few people have tried it. Nobody has ever managed to get anywhere close to what we got up today.
You have to believe you can do these things.
Actually, a few people that have
Me, my boots and I, we don't make it.
I definitely think liquid mountaineering is actually Ulf's brainchild.
It's a new sport. It was not existing before.
You have to run very fast on the water.
Obviously, the first step is the most important. When we discovered, oh my God, Jesus, we're going one step, we're going 2 steps, we're going 3 steps. We're discovering it as we go along.
While we're still on land, we try to get up really speed. Soon we touch the water, we try to get like a swimming machine.
It's not straight into the water, you know.
In a curve, in a slight curve.
And by that bend, you're actually not allowing yourself to sink into the water, and you want to keep that skimming sensation going as long as you can.
What gets us those these shoes?
The original equipment where it first all started was the equipment that would help repel water. But we found some shoes by mistake actually.
So to me, water repellent works like water off the duck's back.
It takes actually a lot of practice, a lot of focus. I think if you don't actually believe that you're going to walk on that water, it's not going to happen for you.
All right, so you have to believe in it, right? So, man, that's a lot of effort, isn't it? And and even then it doesn't work all the time. So let's do a little bit more scientific approach here. So what they're trying to do is essentially remember basic equations. We saw them in beautiful tensor formulas reducing to stresses and shear rates, and here's the viscosity, right? So now I apologize, so my notation is a little weird between these two talks. So now tau is not the time to break up, now tau is a shear stress. And gamma is the surface tension, but sorry, gamma dot is not a shear rate. This is different communities, and so I changed it. I just remember that. That's what it is. And but in basic, the basic idea is if you want to have a lot of stress, you know, you have a given viscosity, whatever that is, water, you need a lot of stress. That's where, 65 miles per hour or whatever comes from, and it's what this guy is. And the lizard may be really good and muscular, but even these athletes, they just can't hack it, right? Of course, you also don't want to sink in, because then you have to pull that leg back out, so that's why it helps if you have shoes that come back. So if the viscosity is constant, you get something really boring like that. Okay. Now you can have liquids that are a little bit more complex. For example, liquids that have a yield stress, okay, but still a nice straight line. And then we could now, that's the game, we can try to do something to the liquid. So basically, I'm saying I'm running out of ideas of what to do to the runner. Let's fill with the liquid now, right? Let's worry about the viscosity, because I can't get the gamma dot with my legs to go to 65 miles an hour. I want to walk on water. I don't want to train 10 years to do that.
Why don't they just wear big shoes? Is this
Yeah,
somehow?
but then they flow. That's cheating. I think within the sport of liquid mountaineering, as described on YouTube, this would be cheating.
Actually, one of my students built big shoes to run on water and tried it out in the pool, and it works. and you don't float, so it made out of metal.
Yeah.
What do you consider the shear stress?
Yeah.
So
So
that matters, and is it the same thing?
yes. Okay. This is true. So
It's the same thing.
yeah. It's right. So for a liquid, the normal stress and the shear stress are not the same, and then it's also inertial effects that one would have to really worry about. So yes, you're right. But why am I talking about shear stress? It's just really simple, because in the rheology community, and we got into that now, people, they have a rheometer, and what they measure is this, shear stresses. And just recently they all woke up and decided to all look at normal stresses, but typically you do shear stresses. So let's just play with shear stresses a little bit. I mean, it's true actually, we need to work on it. What I want to show you a lot of is now plots like this on a log scale, actually on a log scale, because we're going to go over many decades in shear rates, many decades in stresses. And so I just want to get you familiar with this notation. So if you have a linear thing like this, right, that was an offset, and now you plot it down on a log scale, let's say here. First of all, what you want to plot is the viscosity. And the viscosity is defined in my way of thinking about it, is totally silly and simple as the ratio. So no derivative, no nothing. I'm defining it in the standard practitioner's way. You measure the stress, you measure, set a shear rate, you divide through, and that's the viscosity. It's very simple. If you take something like this, of course out here you get your eta, but up here things happen, right, because of this offset. And so then a curve like that will look like this. If you plot it viscosity is a function of stress, where the yield stress would be where this diverges, and the same curve plotted in a slightly different way, namely directly like this, would look like that. Okay? Just familiarize with that, yourself with that. The reason that this blows up is that basically this is almost like solid friction, right? Meaning just that there's no viscous component right near zero, so it diverges, and that's a yield stress. So diverging viscosity is like going towards a solid state. This is what we're thinking about. And then out here, once you shear the map, it flattens out, and then it's your ordinary. So now most liquids that are not pure or simple, like water, let's say, they don't have this line here, or they don't even have that offset, but there could be some power law dependence. And the typical dependence is this 1/2 law here, but it could be anything near 1/2. In fact, it could be anything. But this is a very typical behavior because most liquids shear thin. So as you push them, they actually get thinner, and that's what you want. Blood, good idea, gets thinner. Motor oil, the last thing you want is the faster the pistons go, that you want it to lubricate better. You do not want things to bind. So you want, if anything, you want things that fall maybe a little bit below that line. That's good, that's engineering. You want it to come off the brush. It would be stupid if it's stuck. Now, a shear thinning fluid, therefore, let's say one of these power law versions, would look like this. Now, the viscosity is not constant. And most liquids are either Newtonian or shear thinning. And they have made shear thinning by design because that's what you like. But there are some crazy liquids that are not shear thinning and in fact shear thickening. So that means the viscosity actually goes up as you shear harder. And that's maybe a good candidate for walking, right? I mean, wouldn't that be kind of cool? Okay, so if you take such a liquid and you put it in a pool, you can whack it with a mallet. That's one of my students whacking it. Doesn't even splash. You don't believe that? Yeah, let me show you. This is some of this stuff. You can play with that. Here's a knife and a white liquid. Oh, I should maybe show it to all of you. So you can put that knife in there and then play with it. I have another one for you guys over here. You have to maybe mix it a little bit because it's been sitting for a while. And the good news is that if you put something in there, like this knife, it's yet the liquid is a liquid, so you'll see that. So I have the third one. If you put that knife in really carefully, it sinks in. If you stick your finger really hard, you break your finger. If that was a wooden piece of whatever, you could break it. So what is that stuff?
That feels like it's liquid.
Well, mix it. Mix it. So what is it? This is organic cornstarch. So you can also drop something in cornstarch, and you see momentarily it actually breaks things, and then on longer time scales it actually sinks. So this is also time dependent. There's an interesting complication. Right? So there's a time scale associated with it to come down and be decelerated, but then after a while. Now this behavior, when it falls into a liquid, that then suddenly behaves like a solid. That's shear thickening. And that can be used for all sorts of things, including, for example, what Noel Wagner calls a liquid armor. Wouldn't that be nice if you had a bulletproof vest that is just basically like a liquid under normal motion, but when something really fast comes, it turns into a solid. It helps you prevent you being stabbed. That's what it's actually used for, or maybe shot. So, heck, when I spent a lot of time at various DARPA meetings where people were worried about that, and we originally thought we used that to make our robot, but I showed you in the end, we went back to the grains the last time, right? So we didn't use shear thickening for this. So what is shear thickening? So here's this log scale, log, shear, stress, and viscosity. Shear thinning This would mean there's a yield stress someplace, comes down, shear thins. I mean, it's just because it overcomes the yield stress. It basically starts flowing. And then here, viscosity comes up. And the different curves are for different concentrations. If you don't put anything in down here, if you put particles in, you get up here. So what is cornstarch? Cornstarch is 10 micron particles in water. So it's about 50-50 mix that I made there for you. Right? Now, this has been known for a while, and Barnes, Howard Barnes wrote a really nice review in '89. And if you look at different curves that are now for different volume fractions, so 57 goes to jamming right here, 45% at the bottom, they all display the same idea. Typically shear thinning goes through a minimum, you call it kind of the onset of the shear rate, and then it comes up. And this is log eta, log gamma dot. Okay? And the interesting thing is that this jump can be enormous. So for cornstarch, it is a near vertical jump. Now notice also that this jump location here, where at a certain shear rate, the viscosity goes up or the magnitude moves slowly to the left. So you don't have to push as fast if the concentration is high. Right? Now, so in cartoon form, this is what we're dealing with. Okay? Something that comes down and it jumps up. And typically at some point it goes over here. So what that means is that there is a certain shear rate, gamma, where you can have all sorts of shear stresses. And therefore all sorts of viscosity jumps right up here. Right? And so what that basically says is that, that if you march out here, you increase the rate at which you work, you come to this point and you can't do anything anymore. Your shear rate is not increasing. Your motor is maybe going to die because you would have these enormous stresses. The viscosity gets so high, you can't even churn that liquid anymore, right? So at this point, gamma dot is essentially constant, which means that eta is proportional to tau. So that is just a way of saying if I plotted the same data as a function of tau, I get a slope 1 here. So this is called discontinuous shear thickening. And a vertical jump on this plot corresponds to a slope 1 on this plot.
How would it look like the tau as a function of
Oh, and then it is the original one. This is just like this. Sorry. No, I'll show you in a second. I'll show you the original stuff. Maybe geez. It takes a while. I'll get to real data and I'll show you the real data. But now the question is, can you use that? Can you actually use that now to walk? Right, so now what you want to do is you want to walk fast enough that you get to do this regime because presumably now your viscosity is big enough that it could support you. Or look at it this way, you want to put enough stresses on it so that this thing becomes thick enough that it supports you. Right? And it works, even for people that are not athletes. So, yes, my last movie. Oh. Big pool. Look at this, they used a cement mixer, a truck. So the pool goes up to about here. Notice that there is waves on top. So this is actually not a solid. It is liquid-like unless and until you really hit on it, right? Now, the other thing that you see is it's about waist deep, right? And that means if you don't push on it, you will sink in, like that steel ball I showed you, right? So what's going to happen next is that this guy is being convinced to run halfway in and then just stop moving, right? So that takes, of course, some courage. So that's what's happening. Okay, so how can we understand this? And what I'm telling you now, there are two approaches. There's one out there in the literature that is a beautiful approach that involves, as a basic ingredient, the hydrodynamic interaction between the particles. The liquid is crucial for that. So the particles will interact, attract, in fact, clump up due to basically lubrication layers. Okay? And the other approach is one that is based on purely granular arguments and could get away without a liquid ball. And while this first approach works well for mild shear thickening, what we'll see is that this granular approach is, so far, as far as I know, actually the only one that can give you orders of magnitude changes in the viscosity. So Barnes wrote this paper that I showed you earlier, that I took a picture of, and then he did a huge survey, and in fact he said that basically all suspensions should shear thicken. So any time you put particles in a liquid, in principle there should be shear thickening. It doesn't really matter what the particles are or what the liquid is. It just depends on the right circumstances. And that was in '89, and so what Eric Brown and myself have done recently is look at what are the circumstances, especially for discontinuous shear thickening. So that's the question. What are they? Because if you actually look at suspensions and you buy them off the shelf, besides cornstarch, most of this stuff is actually shear thinning. And industry wants to engineer shear thinning to begin with. They don't like pipes clogging up and stuff. So Noam Wagner, John Brady wrote this very nice review in Physics Today. Again, this is the idea that there's shear thinning, and then there's at some point shear thickening, so this is stress or shear rate, and here's viscosity again. And the picture that is the canonical picture in this business is that here you may have a ordinary liquid, and there's some stratification, and there's a question, it has been a long time, a big question, whether or not you need this to be in flow layers or not. Probably you don't even need that. But then, at some point in shear rate, this thickening emerges, and it is basically the following idea, that the shear rate shoves particles together, and then Brownian motion, for example, allows particles to diffuse away from each other. And if the rate is large enough to shove them together, then lubrication forces will be large enough to bind them together until finally Brownian motion pushes them away. And you form these clusters. They are called hydroclusters. Right, so this is a Peclet number argument. And it works okay, except that you would guess then that the threshold for this would be Peclet number, critical Peclet number, so where you have to push harder together, then the stuff would flow apart. And it just turns out that the Peclet number argument doesn't always work. In fact, there's a big argument as to whether that actually can work. The idea is, and the idea here, furthermore, is that if these things grow and eventually span the system, that is the upper and lower plate, it would percolate across and you could support stresses all the way across, and there would be strong shear thickening. Except nobody has shown that this actually works. And all computer simulations that did this, that maybe Cates and company at Edinburgh, they maybe get 20% viscosity increase, but not order of magnitude. So that's an issue. So here's Eric, and so that's the questions that we're asking. And then let's just focus on this extreme form factor. Okay? So we use the rheometer for this. So here's the suspension, and there are all sorts of things, definitions of the stresses. So the rheometer always returns, so we have to convert some torque into a stress and shear rate from the frequency. And then again, we define the viscosity like this, and everything is in steady state right now, because that's simple type of measurement. Just to give that away, I mean, there may be issues with that, especially if you want to walk. The bottom line will be, nobody really knows anything about the transient response, and that may be a big part of why we don't really understand how you point such. But what about these measurements? So here is stress versus shear. So this is now for you. So as stresses come up, this would be Newtonian type fluid here, slope 1. and that would be viscosity, right, just the ratio. And then there's shear thickening, and then it goes way up. And this is for different concentrations. So you march up with the concentration, get more and more concentrated, and as Barnes said, this thing moves over to the left. And this is about an automatic, maybe even a little bit more jump. It's quite significant. And then you put just a little bit more particles in, and instead of doing that, bam, it's up here. This is data. So now it's independent of the shear, it's frictional. So this is really dense. This is already given you a hint. This is a frictional fluid. This is not an ordinary fluid. And it's a tiny change in packing fraction. So now you might say, well, how do we know packing fraction to 3 digits? Well, we don't know absolute packing fraction to any more than 2 digits for sure. But relative packing fractions we know really well. Right? Now different systems behave differently. Look at this is glass, just ordinary glass in oil. This is cornstarch, and look at cornstarch, how it jumps up here, orders of magnitude. But it does it at a slightly different packing fraction. Now you might say, oh, maybe cornstarch has some wild particles, things that interlock, or it'd be really complicated. That's what we thought too. What is what cornstarch actually looks like? It looks like glass shards. They're pretty remote. There's nothing funny about these particles. Yes?
Is there any rate components to these curves? So,
well, you have the rate right here. So that's what that is.
I guess I mean the rate at which you sweep the shear rate itself. So, for example, each data.
No, this is all steady state.
Okay.
I'm not talking about any transients. Yeah.
I'm going to chase this paper down, but if I look at the details, the drowning motion depends on temperature. Have they varied the temperature and all this?
Yeah, so Noam Wagner has 20 years of papers out there that go into a lot of good detail. It's really lovely papers, and you should look them up. And they are in the Physics Today article by Brady and Wagner. So Brady invented this idea of hydroclusters based on computer simulations in the late 80s as a student. And then Norm did some of the most extensive measurements. His idea was Delaware shear thickening. And he's also the one who turned this into this liquid armor. Really cool. And so what we are now focusing on is one wrinkle, which is this discontinuous shear thickening. So now let me take these plots and just plot them in this other way as viscosities, right? So it's simple thing. I just take the one that was glass right now. So this is the original plot I just showed you. See how it jumps up there. Now I plot it versus viscosity shear stress. This is what we talked about earlier. So this data turns into this data, and the slope that's essentially vertical here turns into a slope that is 1, right? Just too familiar with. So that is discontinuous shear thickening. And notice one thing, it's really interesting, but it is just a little wrinkle, but it's really a deep thing. Different concentrations move things around here. You plot the same data, and you notice that they essentially track each other in terms of stress. There's some sort of onset stress now that does not depend on the packing fraction, and there's some final stress which does not depend on the packing fraction. So that already gives an idea that maybe the way to track this riddle, where this all comes from, is not the shear rate, but it is stress scales. It has to do with stresses. Of course, stress are related to shear rates by viscosity, but this already tells you that one way to do that would be at least a total error, and that's how we got some mileage out of this, all right? So in fact, let's just take that same data on the right, plot it again, here it is, all right? And you see as you march up in packing fraction, boom, it turns into this yielding system. This is essentially something that is a solid down here, and you just break it. And of course it thins, right? I mean, breaking is the extreme case of shear thinning. It falls apart. And now if you plot these stresses, the onset and upper limit, as a function of packing fraction, this is now for glass spheres, you notice something really interesting, that the onset and the upper limit do not depend on packing fraction really, at least over this range. It's a pretty significant range. And so that means you can always start out with shear thinning, and then go into shear thinning as you apply more and more stresses, right? Now, of course, if you go too high in packing fraction, I mean, you jam the system, it becomes a solid no matter what you do. You can always break a solid if you put enough stress on. Fine, that's this transition right here. So this is This is the regime we want to talk about. And so the nice thing is, that's what Eric found, it is the stress that sets the state. So let's talk about that. What about the onset stress? Now I'll tell you about where that comes from, and then I'll tell you later where this comes from. So what is the microscopic origin for these two stresses? And here's a hint. So you take an ordinary shear thickening curve right here, and you turn it into this. Or actually, we started with this curve, yielding, right? And then turned it into this. And what did we do? We just put a little bit of detergent into the sample. Right? So we changed the interaction between the particles. Here they glob together, and then they make a yield stress, they fluctuate, and here they are more independent. The yield stress is gone, and what emerges, what was buried underneath here, right, is this. And that tells me that shear thickening was always there, was just masked by a huge yield stress. The yield stress is in fact so large it sits up here, right, that you couldn't see all this stuff down there. And once you get rid of the yield stress, that is once you get rid of this particle attractive behavior, the yield stress marches down and then you get to see this. Right, so that's kind of the idea that I want to push. Let me push this a little bit more. We're not good with chemistry, so I can't really vary this enough. I would like to sweep through here. But we can do that with electric fields. All particles, glass included, are susceptible to electric fields. So here's the electric field. It's not 2 dimensions, just for show and tell, forms these chains. And if you don't put electric field on this black curve here, shear thickening, right? And now you put an electric field will make the particles stick together. Goes like E squared, an induced field. You march up here. Notice that all of these curves are pretty much parallel, and they are hugging this one line, right? So you increase the yield stress, and you cover up more and more of the shear thickening behavior. Or conversely, if you started from here and took the field off, you recover all the stuff that's actually underneath. So that suggests that, in fact, stresses are a good idea because you can add them. Essentially, you can add whatever gives rise to the shear thickening, that's the underlying bit, and then you add on top of that anything having to do with the yield stress. So maybe a simple additive approach for water. Let me show you one more thing. You can do that, of course, with the magnetic field. So we made some really funky particles at the University of North Carolina. They use essentially how you make ice cubes. You make a nano mold, you fill it with particles, you can make that mold any shape, and then you break out the particles. These are PEG, polyethylene glycol particles. And they are large, they are hundreds of microns, so we made all sorts of shapes. Because initially we thought, oh, it's maybe the particle shape that matters. We made crosses, hooks, anything. Turns out particle shape doesn't matter that much. It is basically the particle interaction for the concept stress. That's what I'm kind of telling you as a message. You can put a mint leaf in an ice cube and then put more water on it, bury a mint leaf in it. You could bury magnetic particles in your little particle in the PEG thing, and then you have a magnetic suspension, right? Now you put that in, magnetic field, they align, and now you see even more beautiful data how adding a magnetic field just moves up here. As you increase the yield stress, you mask, you cover up that behavior. Yes?
It seems as though the shear thinning behavior becomes far less sharp as you decrease the field.
I think they are more or less parallel to me. I don't know.
Previous one, that's more obvious.
Yeah, especially in the previous.
This is shear thinning. I mean, any of these behaviors, right? It's shear thinning.
Yeah.
This is not shear thinning. This is pretty much the formula.
Okay.
So from this, you can make these phase diagrams again, and I don't want to belabor it, but now you have another axis, magnetic field, and depending on where you put your yield stress, right, you can move through this normal behavior, or you can get jammed, and so on, right? So it really works. So this is now what we believe the onset is controlled by. It is controlled essentially by yield stress. But anything that gives you yield stress, magnetic fields, electric fields, chemistry, and as it turns out, actually confinement, if you just put boundaries in, you don't allow things to move, you make it really granular, put them in a stack. It's still a yield stress, all right? And so this addition can work. So what about the upper scale? So again, surfactants give you maybe a little bit of an idea. So now we're looking at the change of this turnover here. And a surfactant, can change the surface tension by maybe factors of 3, 4, 5 or so. And here's maybe factor 3, so it marches down. Okay? But there's something else. And if you just make this cornstarch, put it on a thin layer here in the plane, and then take a ruler or something and slide it along here. So this is fixed boundary here, fixed boundary there. Make a tiny pool of this on a table, a few millimeters tall, and you just slide one boundary along. You notice this is getting shiny, right? Remember, granular materials, dilation, walking on the beach? That means you're dilating right there. That's your halo around your foot. So, no dilation, now it's dilated. So shear in these systems also means dilation, these dense suspensions, right? That was actually an idea that came already up in the 60s, but people forgot about it. The whole literature for 20 years ignored this or didn't want to deal with it. You can actually see it if you look on the side of this shear cell. This is the upper boundary, but there's one guy stuck to the upper boundary. Here's the bottom. You just look at the side, you see the particles protruding as you shear. It's kind of like the drops I showed you earlier. So as you shear, this thing can't go up, it can't go down. These are hard boundaries. All it can do is go out. And that's where it goes. It dilates a little bit on the surface. So this gives us an idea that once you shear, you can use menisci. All right? They set a stress now. And the confining stress is exactly what we talked about before, with some prefactor that depends on wetting and whatnot. All right? And so now what we say is that when you shear so much here that your dilation wants to push this out, that it overcomes that confining stress, well then you can't have shear thickening anymore, right? Because the material can actually expand to it. So if shear thickening is essentially due to frustrated dilation, then what keeps dilation frustrated is the fact that you got that pressure. Once things push out too far, then the particles are not close enough in contact anymore, and you don't have shear thickening. Right? There's a question.
You talked about Reynolds dilation before.
Yes, that's the same thing.
That's the same thing. I mean, how does the liquid change the thing compared to?
That's a good question. So why do you need the liquid for this? Keep that in mind. Now, there's one experimental reason. If I don't have a liquid here, the stuff just falls out. That's why I need a liquid. But what if, I could put a wall there? Do I really need the liquid for this idea? So, what is the idea? I got grains in a bucket where I have soft balls. I'm turning here so that they get dragged along. They want to shear, but they can't shear until they dilate. Now they can't go up because they keep the lid down. So all they can do is they can go out that way. Once they go out that way, but they are held back, there's a stress. So that's my shear stress. Now of course if they go out too far, maybe they pop out, they just fly out. Well then, cool, then I don't have a shear stress anymore. Then I'm over the limit for shear thickening. So if that's really true, then the upper end should be set by this number, right? So now what Eric did is went through the literature and looked at anything that we can find. Most of the stuff published actually you don't find the numbers because in the typical rheometer you use colloids and gamma over A, where A is now a colloid, not a suspension, so sub-micron particle. Well, gamma over A is so large that rheometers tend to break before you ever get there. So there's not much data on this. This is a little bit up here, but everything follows pretty nicely on that line, which says that tau max goes like gamma over A. Right? And even the prefactor we have an gamma on, it's about 0.1. So that works really, really well. So here's the idea then. That in the original picture, down here you would form these clusters by Patelet argument. And in this picture, basically what we're saying, you move this upper boundary, and then there is dilation. And if the dilation is kind of frustrated by confining stresses, well, then there's so much grinding of the particles in there that it gives you a lot of shear stress. I mean, you can break the particles or you can break the boundaries. Once you do either one of those things, then shear thickening will cease. So if you whatever is softest, the boundaries are the particles will set the upper limit. And one other thing that comes out of this, if it's really this granular picture, then there is a direct correspondence between the shear stress here and the normal stress. In fact, it should all be frictional. It turns out that people don't measure this, usually. And furthermore, this picture, if I can understand it right, predicts a negative normal stress. Actually, hydrocluster picture predicts that if they form, the plates get sucked towards each other. Now, if you do this experiment, here's the normal shear thickening curve. Here is the normal stress measured at the same time. This is our resolution limit. So let's say the shear thickening regime right here. Nice, big, huge, positive normal stress. Very frictional, granular. If you take the ratio of the two, that's what you get. This is sliding friction. And this is a frictional fluid. This is not a viscous fluid. So this gives you a hint that these dense suspensions are actually quite granular. So now if that's the case, what do you need the liquid for? Other than this confining pressure. You might as well take the liquid out, right? And you can confine it. That's what Eric did. So we made a little shear cell where we have hard walls here, particles, and then turnout rheometer. Now this wall is not totally hard because if you made everything hard, you couldn't turn it, right? It would just slip or break. So we made this now the softest one. And here's the data. Beautiful shear thickening data for different concentrations. Now they are all close to jamming, right? This is perfect discontinuous shear thickening. Gorgeous. So you don't need the water for this main effect. And if you look at that from the side, this is not the same as looking inside, but just from the side, you see that down here, these are now suspensions that settle, right? So there's just a liquid there. Of course, nothing happens except when totally shear in the liquid, so that's fine. Then here you start to involve a few particles, a few layers, and eventually if you were above here, which I don't show, then it would bulge out. I mean, I showed that earlier, and it just dilates. So as you run up that curve, you involve more and more layers until you run out of space. So now if you figure out, or try to figure out what that would mean for the onset, so in this case it's gravity, right? So that's this. Basically what I'm saying is, if that's true, so this is just a liquid layer here, so at some point, once I involve particles, I should write up this curve. So how much shear do I need to pull particles up and involve them in the flow? You can do that, and you can just estimate the stresses here that involve some friction, that involve a difference in the specific gravity that we can set. So for example, for different glasses and different solvents, and then some geometry that you can actually find in this paper here. Then you see that the stresses, of course, increase with the particle diameter. The bigger the particles, the more you have to shear until something happens. So that would say that the onset stress should just scale with the particle diameter, linearly. Right? If you want lots of shear thickening, you want to be to a small particle diameter now that you get a huge range, that your onset stress is really low. Of course, you want to make sure that your upper stress is really high, which is great because you know it's gamma over A, right? So A is tiny, so this would be the right thing to do. The only problem is with colloids that then chemistry starts to matter. You know about a micron, you have Brownian motion. That's often happening. You have electrostatic interactions, and they all come into play. And there's lots of literature on that. And the unfortunate thing is that these onset stresses now, they scale like 1 over A to some power. All right, so the smaller you go, the higher the onset stress. That's no good. You couldn't even see them shear thickening. And then this is what we did here with electric field completeness. So in one case, you know if you go too small in size, then interactions get the new stress up. If you go too large in size, then gravity will settle it out, and that's the good. So there's an optimum. And so if Eric puts this all together, and you can look it up in a recent paper here from that, there's a certain sweet spot right here, right? These are all these different interactions. And it just happens that cornstarch, and this is really wonderful, is right at the right spot. Right down here, we see the biggest range in shear stresses. And you can buy it in any grocery store. Everybody has it. It's benign, it's just water. So it works. It would work with other stuff too. Okay? So I'm done. Just a couple of slides to wrap this up. So all right, so how do you want to walk on water? Whatever you do, you have to do fast enough or generate enough stress momentarily, right, to get into the shear thickening regime, because this doesn't work, I think, or not for me. This I've tried myself, works like a charm. And the other thing, of course, is that this does not work in part because we didn't put any particles in the water. They put them in, but they needed a cement mixer truck back there. We do it every year. We do a Christmas lecture for the public, and we do these experiments. And we just take a bathtub full. It breaks my back to just mix it. So I bought for my lab a real cement mixer. Because it takes half an hour instead of 3 hours to mix it. Much better. Okay, so here are the conditions then for discontinuous shear thickening. The last slide. What we think you need is really dilation. You need a confining stress that frustrates the dilation. And that has to be really the dominant stress in the system. And otherwise you can't run up high enough for shear thickening. Of course, the onset of shear thickening is the yield stress, and that is determined by particle interactions, chemistry, things like that, and that needs to be small. If these conditions are fulfilled, you see a huge range of shear thickening. And for cornstarch, by the way, it works because cornstarch is exceedingly high-risk copper. So there are no double layers, no funny electrostatic interactions. It loves water, and you put it in water, it's totally happy. So that's why it goes from really low to really high. And the granular picture can explain a lot of things, including the positive normal stresses. And I bet that the hydrocluster picture is there, but for these cornstarch, like discontinuous shear thickening systems, it is overwhelmed by all the other stuff, right? And there's a really nice recent paper that's going to come out in Science in a couple of weeks by the Cornell group, by Itai Kohn and his postdoc Chang. And they're the first to actually image with confocal microscopy those hydroclusters, or the beginnings of it. So we're almost now there being able to see some of them, but this can only explain maybe 20% of the increase. So you really, I think, you need this picture to do that. And just so that you don't think, I mean, for full disclosure, right? Transient response people don't know about. That would be important for really walking. And so this is for you guys to think about this. I don't know. And an obvious thing, that respect under the rug. You walk on this stuff, you do this. I do experiments in the lab, I do this. That doesn't have to be the same. And, you know, who says? And in fact, we are doing right now compressive and extended measurements. So I saw some beautiful data, I guess you showed it, of extending column of cornstarch, and it breaks apart, of course, also like a solid if you do it faster, right? So the stresses under compression and the stresses under tensile loading are actually much, much harder, much, much larger than the stresses you get from shear. So this is the last curveball I'm throwing you. All the stresses, if you look up the notes that I show you, beautiful measurements by area, they're actually too low, shear stresses. They're hundreds of Pascal, they're too low to support the person. Right? So if you want to walk on it, all of what I told you is probably okay, but in addition you have to worry about compressive effects. And I bet you, this is just my bet, it's going to be granular again. And it has to do with what I told you in the first lecture. It's basically pushing on something and the force shifts coming down. But anyway, with that, I'll thank you. Yes.
When you get rid of the water, how do you prepare the granular system? Do you just pour it in?
Just pour it in. So that's, you know, maybe stir it up, pour it in, and not crystallize, right? So it's a 3D system, so it's actually hard to crystallize by just pouring it. Yes?
But when you use the PEG particles, are those the softest thing in the system, or are the boundaries softer than the PEG particles?
No, in this case, the boundaries are probably harder. No, actually, I think the particles are harder than the boundaries.
So have people done things with soft particles?
Yes. And now I would have to remember, and I don't right now, that would be good for me to recall right now, but I don't. So for example, why don't emulsions shear thicken? And the quick answer would be they are too soft, right? Now if you could make the boundaries so soft that this stress is still in the same range, then you I guess you might want to see that, right? But you could see it. But you need fairly hard particles to do that. Let's have comments.